was Nikolaus, third talk, higher categories and algebraic theory.
Yeah, thank you. So in the process of this lecture series, what we did last time is we indicated how to see that if we do algebraic K-theory of the complex numbers and we complete at a finite prime, this is equivalent to topological K-theory. This is an equivalence of E-infinity ring spectra. And then for Fp bar, the algebraic closure of Fp, we saw, at least I sketched how to see that this is actually equivalent to topological K-theory. And here it's important that L is different to P, so away from the prime P. And in fact, I cheated a little bit. I said this already last time, that for this actual thing we needed this GABA result, but also you need a localization result, which I'm going to get to next time when I talk about Whitehausen K-theory. So we use a little more than just the group completion K-theory here. And in fact, actually this is, turns out that algebraic K-theory of algebraically closed fields only depends on the characteristic. So this tells you already a lot about algebraic K-theory, and these are like the topos points in the étale topos. Well, actually the topos points in the étale topos are strict Henselian local rings, but let's not get to that. So finally, we proved that for a commutative ring or ring spectrum, K of R is an E-infinity ring spectrum. Okay, and today I want to focus a little bit on the case, the P completion, where P is a characteristic, so that we finally understand that object in total. And one of the tools to do that is that had already been used by Quillen is the technology of lambda rings. So chapter 4 is lambda rings and polynomial functors. And a much better tool, of course, or like way more powerful tool is trace methods, but I don't want to talk about trace methods in this lecture series. Okay. So now again, R is a commutative ring, and here it's important, R is an actual ring. Ring spectra are not allowed anymore. So what I'm going to say doesn't work for ring spectra. So if we do that, we have functors called lambda n, which go from the category of projective R modules to itself, and well, it's exterior powers. So it will just take m to the, takes the n-fold tensor product of m, and you take the actual co-invariance, sigma n, where sigma n acts through signs. So that's the exterior powers, and the point is these give rise to operations little lambda n k naught r to k naught r, called exterior lambda operations here. And this is not entirely clear if you think about this. This is not an additive operation, right? If I input like a sum, I get a more complicated formula for that. It's not entirely clear how to extend that to the group completion. So there is a formula for what happens for the sums, and one way to get that operation is just to say I still want to have this formula here, and then you can make that happen. But let me gloss over this point, because the upshot of my today's talk is going to be a different way of getting these operations very naturally. So let's just assume we have to find these operations, and then there's the following theorem, and so this has several parts. So the first part is due to Grothendieck, is that, K naught R with these operations lambda n forms a lambda ring. A lambda ring. And I'm not planning to define what a lambda ring is. So a lambda ring is a ring with such operations such that there are formulas for the lambda of the sum of two elements, lambda of a product of two elements, and like the iteration lambda of an element. And these formulas are highly non-trivial. They're expressed in terms of certain universal polynomials. And in fact, it's a very rigid statement to prove that something is a lambda ring, and I personally find the proof, the proof given not very enlightening. It's not an easy theorem. Okay, so this forms a lambda ring, but one consequences of being a lambda ring, in particular, it admits Adams operations. Adams operations, psi p, and these are now ring maps, k naught r to k naught r, that are Frobenius lifts. Frobenius lifts. So what that means is if you reduce this mod p, it's the Frobenius of the ring k naught r mod p. Right, and k naught r mod p is a ring of characteristic p, automatically has a Frobenius. And in fact, you can recharacterize lambda rings, if you say that correctly, exactly as having for every prime a Frobenius lift, and they commute. So in fact, this is verbatim true if you're if you're torsion free, and if in the presence of torsion, you have to say that a little bit derived. So it's a derived Frobenius lift for every prime. Okay, so secondly, if R is characteristic P of characteristic P, so that the Frobenius makes sense, then this P's Adams operation, psi P, is actually the same as taking the Frobenius of the ring, the self-morphism of the ring, R to R, and then I can just get an induced map on K0 by pushing forward with respect to this homomorphism. And so that's the second part of the statement. And the third part is, this is due to Hiller and Gratzer, and I mean it's attributed to Quillen, but not published by Quillen himself, that, I mean, these structures extend to higher K groups. I.e., these are lambda rings. Well, but what is the multiplication with zero multiplication? I mean, this is a poor way of stating what I want to state, but let me say multiplication. What they really prove is these operations psi p and lambda p that are operations on K0 lift to the space level. And as a result, if you map any space into the K-theory spectrum, in other words, you form the cohomology theory represented by that spectrum, then this actually doesn't only give you a cohomology theory as well as in rings, but a cohomology theory as well as in lambda rings. And now you specialize this to the case of the sphere. So if you evaluate this cohomology theory on the sphere, you get a copy of KNR and K0R, and KNR is a square zero ideal. So the only thing that we really need is it's a lambda ring with respect to the zero ring structure. But it's a non-unital ring with zero rings. In particular, this means that the Frobenius is zero, right? Mod p. In other words, this psi p is an operation which lifts the zero map, mod p. That's what this means. Okay, does this make sense? Again, this is a poor way of stating the algebraic structure that you actually have. And so the proof of 3, and I'm going to prove that in a better way today, comes down to just writing down these operations lambda p and psi p on the space level, on the K-theory space level. Note, these are not stable operations, so they can't be spectral maps. So you write down operations on the space level, and then you prove that they satisfy these lambda relations, these universal polynomials, up to homotopy. That's what this is equivalent to. And the main task of my talk today is I want to lift these to the space level, but such that they satisfy a highly coherent version of these lambda operations, lambda relations. And this is a question which I guess was asked by several people, and it's not entirely trivial because these lambda operations are just universal polynomials. It's not that these hold on the level of categories. So it's not entirely clear how to give a homotopy coherent version of these lambda relations. So the upshot of today will be I give you these higher operations and I define what a spectral lambda ring is. And then K0 and these statements will be consequences of that. But let me first give you a corollary, which is very useful. So if R is a perfect ring of characteristic P, so meaning that the Frobenius is an isomorphism, then I claim that K star R phi P complete for star larger 0 vanish. In other words, there's no higher K theory at the characteristic. And why is that? That's because we just said by the fact that these lambda operations exist, we know that psi p is on higher homotopy trivial mod p. Right, but at the same time, I said it's the same, psi p is the same as the geometric Frobenius, which is an isomorphism. So it's also an iso. Well, but that means the groups have to be trivial mod p, hence trivial after p completion. And really, I'm slightly cheating here because you want to derived reduce mod p, but this is exactly what the lambda ring structures let me do. This is the difference between being a Frobenius lift and being a derived Frobenius lift. This is exactly what makes this argument then work. Okay, so in particular, this tells us that if we want to compute k of fp bar at the prime p, this doesn't have higher homotopy groups. Right? So this is an Eilenberg-MacLane spectrum on the p-adic numbers. Well, we already know what is in degree 0. It's just the integers and then you p-complete. So it just tells us that as an E-infinity ring, it's an Eilenberg-MacLane spectrum. So in particular, we can now totally write down the spectrum fp bar integrally. So it's given by, well, you have all the L completions, Ku completed at L, and then you have the Eilenberg-MacLane spectrum Hz, and here you go L unequal P Hz L, I guess. Well, this is just a bottom cell projection. So as an E-infinity, this is a pullback of E-infinity ring spectra. And this totally describes the structure in the K-theory spectrum and the E-infinity ring structure and everything you want to know about the spectrum. Sorry?
This identity over here happens before p completion. Now you're asserting that psi p is...
Right, so I'm claiming that after reduced mod p reduction, so you know, if I have an abelian group and I derived mod p reduce, then it's still 0. And so this is a statement, you know, this is a statement where you really want to interpret, first take the p completion of the spectrum and then the higher homotopy groups. And then you can test that after derived mod p reduction. So you're right, so there's this little subtlety. But for example, if we're p torsion free, you know, I mean, really you can prove a slightly stronger statement that these higher homotopy groups are uniquely p divisible. Right, which also implies this statement. Okay, are there other questions about that?
That statement so the statement about fp bar, that was in Quillen's original paper, right?
Right, I mean, Quillen computes the homotopy groups of that, but not the spectrum. So here's an identification of this as an E-infinity ring. It's a stronger statement a priori.
You have a map, no? So
well, part of the point was to construct a map. Like part of the hard work we went through was to construct an actual map. So this is, I mean, and in fact, actually now by Galois descent, I mean, we can sort of also describe FP now. I mean, we know sort of from Quillen's computation that we have Galois descent, and we know exactly how the sort of absolute Galois group acts. So we can actually give an identification of K of FP as an E-infinity ring along the exact same lines.
Okay, so the corollary was sort of you get from what you're saying. Now we have the map, so that's sort of the
right. I mean, last time we had to use this theorem of Gabor to produce the maps, right? So this is somehow the Brouwer lift. You know, Quillen constructs the Brouwer lift on the level of homotopy, or maybe it's the space level, but not on the spectrum level. I mean, you know, I'm not saying that I prove anything which Quillen didn't know, but I'm just presenting it in a slightly different way.
Well, it's just,
Super. Ah, okay. Good, but so the point is, you see, just formally from the existence of these lambda operations, we already can deduce that the higher K groups are trivial. So having a lambda ring is a very rigid structure. And in fact, Gillet and Soulet and others have drawn like really spectacular consequence of just having these lambda ring structures. So now let's pause for a second and see how these lambda ring structures arose. Like here, I just said there are these operations. But for example, you could like look at other functors like any Schur functor, or just take the symmetric power or stuff like that. In some sense, we would like to say for a certain type of functor we get an induced map on K theory. Right, and it turns out this is true. This can be done. And I mean, this tells us something about group completion which I didn't know and I was totally astonished by. So which I want to explain now. So let me start with the following definition. We have a commutative group M, so this is ordinary land, and a commutative monoid. So this is really like in sets A, and we have a map F from A to M. And by map, I really mean map of sets. And this is called polynomial of degree less or equal n minus 1 if the n's cross effect, which is a function in n variables, a1 through an, and is defined to be I take the sum over all subsets, the set with n elements, 1 through n. Then you do -1 to the cardinality, and then you say f of the sum I in U AI. Well, that's the nth cross effect, and so I say the nth cross effect vanishes. Okay, that's the definition of what a polynomial map is. And in fact, this is just supposed to capture what it means to be a polynomial. So here's an exercise which helps you understand this definition. It just says that polynomial maps Q to Q are polynomials. I mean, I'm calling a map polynomial if it's a polynomial map if it's polynomial of some finite degree, and so the claim is that these are exactly polynomials. So it literally captures, but what are polynomial maps? Nomial maps Z to Z, it's a little more tricky. So these are all polynomials with rational coefficients which have the property that they send the integers to the integers, and it turns out they are all of the form I equals 1 through n ai for some integers ai, and then like binomial coefficients x over I. Okay, that's a little exercise in number theory. I mean, but the second part is a little mysterious, but the first part of this exercise is really instructive. Okay.
Can I ask, so this
Sure.
map F A to M, is that supposed to be a map of monoids? Or?
No, that's just a map of sets. That's the point. So, like polynomials of degree 1 somehow correspond to affine linear maps.
Okay.
And then in higher, you know, it's like, think of a polynomial from Q to Q that will not respect the additive structure of Q. But I mean, this is saying there is still somehow a formula what happens to the addition, but it's kind of encoded in a little bit of a tricky way. Okay. So, and here's the fact which I was really amazed by when I learned it. So it's due to Parsi in the 70s. And it says the following. You know, group completion of an abelian monoid was the universal monoid which received the map. And this is telling us that polynomial maps out of the group completion M into, group completion A, or did I say this the wrong way? Oh, no, I said it the right way, I guess. I guess I wanted to say it the other way around. Well, anyhow. Okay, now I try to stick with it. Probably not going to work out. So the claim is as a canonical map into polynomial maps from A into M, right, just by restriction along the group completion map. I mean, you just have to figure out that if you postcompose a polynomial map with another polynomial map, then it's again polynomial. And the statement is this is a bijection. So in other words, what does this mean? This means group completion is more universal than you would think. It's not only universal for additive maps, but for polynomial maps. And I mean, this is a really cool fact. And here's the proof. So, first of all, you figure out the following. So if you have a polynomial map from A into M, you know, for every map from A to M, I can just extend to a map over the group ring, an additive map over the group ring. I mean, you know, this is just as an abelian group, just a free abelian group, and it just sends the base element A to M. And so the claim is that this is polynomial of degree n, exactly if this factors over the n plus first power of the augmentation ideal. I in the group ring is the augmentation ideal. Augmentation ideal. So that's not hard to see because you can we explicitly know a set of generators of the augmentation ideal, and then you can just reform. I mean, this is just a reformulation of this definition, which is somewhere up there of the cross effect. Okay, so this is part 1. And once you know that, you just have to check that the map from the group ring mod the n plus first power of the augmentation ideal into the group completion is an iso. And why is this true? So this is now a map of rings. And because this is a group completion, it just follows that this is the localization at the elements A. So in other words, we just have to check that the elements in A are already units. Because, what does this mean? The element A has inverse we can just write down an inverse in this ring. And what is the inverse? We just take 1 minus 1 minus a to the n plus 1 over a. Okay, so what is this? This is a polynomial in a, and because all the terms are divisible by a, I can just quotient, right? And so what happens if I multiply that with a? What do I get? I get 1 minus something in the augmentation ideal. So that's the inverse. All right, that's the proof. Okay, so again, this tells me that the group completion is more universal than you would think, and this is what we want to take advantage of now. So we want to say more maps give rise to maps after group completion. And in order to do that, we have to characterize those functors of categories which somehow give us polynomial maps on K0 or on iso classes. So let me, this is a definition of polynomial functors. And this is due to Eilenberg-MacLane. And really, I mean, it's most natural to state that for stable infinity categories in terms of n-excisive functors. But let me formulate that in the language of additive categories. So A and B are additive infinity categories. For example, ordinary additive categories, which are idempotent complete. Right, so that's a sort of class of categories. I mean, all of these have in particular direct sums. So I can take direct sum K-theory of those. Just take the direct sum as a symmetric monoidal structure and take direct sum K-theory of those. So a functor f a to b is called polynomial of degree less or equal n minus 1 if, and now we want to make sense of that cross effect, so really the same formula works, but let me write it in a form where it's clear that it works. So what I want to say is dA1 dAn f is 0, where dx of y is just defined to be the functor which is the fiber or the kernel of, dxf, for any functor f of x plus y to f of y.
Small f is the capital F?
Small f is the capital F, yes, thank you. So that's an idempotent, because y is an idempotent in x plus y. So this fiber exists because I said it was idempotent complete. So that's really like a form of subtracting this from that, which makes sense in this generality. And then if you spell out what this actually means, it will exactly come down to this formula and tell you why the minuses make sense in this formula. Okay, good. And well, the definition is maybe not really helpful, but there are some obvious examples. For example, the claim is that the functor lambda n from proch R to proch R is polynomial of degree n. This is exactly one of these polynomial functors. Similarly, the symmetric powers, or for example, also the tensor product functor from proch R cross proch R to proch R is polynomial of degree 2. Similarly, the direct sum functor, and so on and so forth. So this somehow captures the phenomena that shows up if you sort of do multilinear things and you sort of plug in a single variable. Okay. Other questions about the definition of polynomial functors? Okay, so what is the point now? Almost by definition, a polynomial functor of additive categories gives rise to a polynomial functor on isoclasses of objects. So the corollary thus is that K-theory K0 extends to polynomial functors. So what do I mean by that? So let me denote the category of additive infinity categories and additive functors by cut infinity add. Additive infinity category and additive functors. So K-theory was a functor, K0 was a functor from here to the category of commutative groups in set. Maybe I should. Sorry, just to be consistent with notation. And then this embeds into a bigger category, cut infinity poly, whose objects are additive infinity categories and functors are polynomial functors. Okay, and now the claim is that there is an extension into the category of sets. Or just forget. Right, and I could say a little bit more that these are still, I could make a category of commutative groups and polynomial maps, then it would be clear how to do that. Is this clear that this immediately follows? Because again, a polynomial functor of categories gives rise to a polynomial functor on isoclasses, and then group completion just extends over these more general settings. Okay, so this is something which I find really cool, because now we can just say, well, lambda n is a polynomial functor, hence it gives a functor on K0. And it's not super explicit. I mean, you know, you still have to say what lambda n of m minus n is. And it just says there is some sort of formula. This is what being polynomial captures, and then you can just use this formula somehow. That's what this informally says. But the proof, of course, uses this Parsi result. Okay, cool. So here's the theorem that we prove, together with Clark Barwick, Thor Glassman, Akhil Matthew, and myself, prove the following theorem, that the functor omega infinity k extends to a polynomial functor. In other words, I have this exact lifting diagram. Here's cut infinity add. I have this functor, which is K-theory, which goes to spectra, or rather connective spectra. And again, I have this functor into polynomial functors. And here I have omega infinity, which goes to spaces. And so the statement is that it extends to a functor here, which maybe I just denote omega infinity k. Okay, that's the theorem. Particular, this tells you that for every functor lambda n, you immediately get a space level map. And this can, of course, not come from a map of spectra, again, because it's not additive. So let me just relate that theorem. I mean, the proof of the theorem is actually not hard once you formulate it like that. So because what you do is you can just look at polynomial functors which have the property that point-wise they take values in infinite loop spaces, like E-infinity spaces, and then you just produce by abstract nonsense a universal such functor, and you get a map from the initial functor, like from the upper left to the lower right. And then actually you just have to prove this is an equivalence, which essentially comes down to a Parsi-style argument. Yes?
This is a property of K, which is a composite of three functors, or really of the group completion, which was the middle of the three functors?
So in some sense, this is a property of the group completion, but the point is the following. So why I formulate it like this? You know, being a polynomial map for a map between sets was just a property. Like if you had two monoids, being polynomial was a property. If you want to say that for E-infinity monoids, and it's really going to be extra structure. But if you start formulating it with additive categories, it remains a property. So probably there's a way of sort of setting up a category of E-infinity monoids and polynomial maps, and then just saying something like along the lines that you want to say. But I think just for a lack of, I didn't really, I mean, this statement is just clean as it is. And there's possibly stronger theorems which imply it, but the formulation would also be more complicated.
And the statement that's behind this for E-infinity monoids, would that work in arbitrary additive infinity categories, or is this specific to E-infinity spaces?
Ah.
No, of course I have commutative monoids in mind.
Right. I don't know at the moment. It's an interesting question. Let's talk about it later. I'm not sure. Okay, so let me make some remarks about that. First remark is, in particular, we get maps lambda n from omega infinity kr to omega infinity kr, right? Just from these things. And these have been constructed before. I mean, this is exactly what I was alluding to at my initial theorem, like this work of Hiller and Gretzer and Grayson also notably has given very nice models. But the point is, all the techniques that I used there were somehow use some plus construction or something like that. So this will at most give you some coherence on the homotopy category. It's good enough to deduce that the homotopy groups are lambda rings, but it's nothing highly structured. So the main content of that theorem should be somehow, this is like as highly coherent and as nice as you want it to be. It's actually an infinity functor. So that's somehow, and sometimes the content is really the coherence between functors and not like the existence of a single functor, even though it also implies that, of course. Okay, so
Actually, version, as you just alluded to in the above case, where I replace spaces by spectra with polynomial maps.
well, if you tell me what a polynomial map between spectra is, probably. Right, Björn?
Does this shed any light on so with regards to the Adams operations, how many times they deloop or anything like that?
Right, so actually it does not, but I mean we know that they deloop either once or twice. I guess we can abstract that they don't deloop 3 times, and so Grayson do loops it once. And this is actually, so what I'm going to spend the rest of the lecture like just exploring consequences of that. But that's actually one of the open questions in somehow relating that to highly structured versions of Adams operations. So let me pause that for a bit and like sort of come back to that later. Okay, then I can formulate a precise conjecture, but which I can't prove at the moment. Let me first make some more remarks. So I'm actually promoting to forget about the K-theory functor at the top and just consider omega infinity k as a functor from polynomial maps to spaces as the new K-theory functor. And so why is this reasonable? Because a priori you could think, well, now I've totally forgotten that I actually had a spectrum. I just remember the space. But this is not true, because for every additive category I exactly have this functor. And this immediately, just if you only knew the existence of the lower functor, would equip omega infinity ka with an E infinity structure. Hence a connective spectrum. Right, and also, like all the structures, like ring structures I've like discussed before, are also stored in this functoriality, because this makes, well, I should say a commutative monoid, E infinity monoid, or an infinity group. And this would just make this an E infinity ring spectrum, or the underlying space of an E infinity ring spectrum. So all of that is just stored, so if A is symmetric monoidal. So everything, all these structures I just said before, in the case of additive categories, are just stored in this polynomial functoriality. And was there a question? Okay, the third thing I want to say is that, I mean, maybe I'm not going to come to that, but really there's a variant for stable infinity categories. Stable infinity categories and n-excisive functors. Just because I formulated everything in terms of group completion K-theory, let me stick with that for today. Okay, good. So now to answer Björn's question. So far I've only given you polynomial functors which are sort of very universal. Like for example the exterior powers. These like exist for every ring. Right? But if you give me a concrete ring R, then there can be way more polynomial functors from branch R to itself and those which somehow exist for every ring. And moreover, it can happen that these don't base change to higher rings. So what we want to do now is we want to sort of distill the essence of those operations which universally exist for every ring. And fortunately, this has already been done, and this is due to Friedlander Suslin. And that says the following. A strict polynomial functor proch R, proch Z of the integers to the n into proch Z to the m. So I just allow n copies of proch Z, and m copies of proch Z is a scheme enriched polynomial functor. Nomial functor. And I'm going to spell out what this means in a second. So while I erase, let me just explain what this means. So there's a canonical enrichment of this category over the category of schemes. So the Hom spaces are in a canonical way schemes, and this is a scheme enriched functor in the sense of enriched category theory. It's a dense way of saying what that is. But using the functors of points approach, we can just spell out what that means very explicitly. So let me do that. So that is for every ring, so such a scheme enriched functor equivalently described by for every ring R a functor, a polynomial functor, polynomial functor from proch R n, maybe I call that FR, to proch Rm, and equivalences. Well, FR, I can just input an R module blank and then tensor up. So for every, I'm finishing this in a second, for every map of rings, and ring means commutative ring, commutative rings. I'm really commutative here. Map of rings, commutative rings, R to S. I can just take FR and then base change up to S. And I say this has to be naturally isomorphic with the thing where first base change up from R to S, and actually I wanted to make this a blank, and then consider that, and which is compatible with, are compatible with compositions, meaning that once you input a composition of maps of rings, then these equivalences have to be the composition in the obvious way. Okay, so this is really like saying literally that's exactly the thing which exists for every ring by definition, but somehow this scheme enriched point of view is maybe a little slicker way of saying that. Okay, good. And so what we're going to do now, we want to sort of this by the polynomial functoriality of K-theory, these are the things which actually act on all K-theory spectra now, pretty much by definition, right? Because they give us a polynomial functor for every ring. Okay, so what, and I want to say that in a somewhat structured way, and in order to do that, I'm going to use the language of algebraic theories in the sense of Lavier, or actually an infinity version of that. So TFS, Fs for Friedlander-Suslin, is the infinity category, whose objects, means objects are really the natural numbers, but let me think of those as proch Z to the n. And what are morphisms? So I want to say that morphisms are just strict polynomial functors from proch Z to the n to proch Z to the m. But now what I want to say, this is actually an exact category. I mean, and so this is a gadget where I can take K-theory off. And so I want to take the underlying space of that K-theory spectrum. So strictly speaking, this doesn't make sense. So a priori, you could consider this as an additive category and take group completion K-theory. But the problem is, even though in proch Z all sequences split, this doesn't mean in functor categories all sequences split. So really, I'm going to sort of ignore that point here. There's a sort of exact version of K-theory or Waldhausen K-theory that one has to use here to make sense of that. I'm going to come to that next time. Okay, but anyhow, this is the definition. So this is an infinity version of a Lavier algebraic theory. This is just a category whose objects are the natural numbers. Every object is an n-fold product of this given object proch Z1, and these are the mapping spaces. Okay. And for this, I'm actually using that K-theory preserved products, one property which I've proven like 2 lectures ago, I guess. And then I say a spectral lambda ring. Lambda ring is a product preserving functor well, let's maybe call it A tilde from TFS into the infinity category of spaces. An algebra or model for this algebraic theory. Okay, so that's the definition. And
Is it still the product, or did it just mean?
yes, it's still the product. So you might object what this has to do with spectra, and I'm going to address the point in 1 second. So the essence of what I've explained today so far, and a little bit more, that Kr, or omega infinity Kr, is a spectral lambda ring for every ring R. And I'm committing the usual abuse of notation. So a spectral lambda ring is really a functor, and I'm sort of notationally going to identify that with the value at 1, or the category proch C. So this is like the value at 1 of such a spectral lambda ring. So that's kind of roughly, I mean, this follows from this polynomial functoriality. Okay, so why do I call these spectral lambda rings? So the first thing is that, of course, there are these operations plus, as we said before, this always exists for every category. So this is like a strict polynomial functor. And there's tensor proch C. I'm just going to list some operations that always exist on these spectral lambda rings. And then there's the operation which is tensoring with M, which goes from proch Z to proch Z, and where M is an element in proch Z. So that's a strict polynomial functor. In other words, on every category of modules, you can tensor with the projective modules over the integers. And finally, there are always these operations lambda n, proch Z, proch C. And so what do the first three give me? The first three make omega infinity lifts to a E infinity KZ algebra spectrum. So because I can add and multiply and act with KZ, and these interact in a certain way, you can use these to prove that this means it lifts to an E infinity KZ algebra spectrum. Every such polynomial functor. And this gives me extra operations, lambda n from, I mean, actually, I guess for every, this is true for every spectral lambda ring. I'm just spelling it out for omega infinity Kr. So this gives me these self-maps of omega infinity Kr to itself. So the question now is, and I mean, the point is, by definition, these have to satisfy a lot of coherences, right? I've just saved these into the category. And now, of course, the whole success of this project now rests on the question whether we can understand this category, at least to an extent, right? So, I mean, so far this is pretty formal. I mean, I think there would be a result, but we would not be happy with it, I guess. But the point is we can, or we can say at least a lot about this category. Okay. What do I want to say? This is the next theorem that we prove. So the first thing is the endomorphisms of 1 in that category. That's an E infinity ring, right? Because endomorphisms of every of the object 1 in an algebraic theory are automatically going to be a commutative thing. So the spectrum, and this is actually the spectrum K of strict polynomial functors from proch Z to proch Z. Well, this sometimes tells me the
commutative theory if you want the endomorphisms to be.
Well, I guess the tensor unit in every symmetric monoidal category is automatically like commutative thing, because 1 is the tensor unit with respect to the Cartesian product.
Yeah, but this is a special Labier theory which actually is commutative in the infinity sense.
Wait, every Labier theory has Cartesian products, right? It's symmetric monoidal. I mean, what is the definition of a Labier theory? It's a category which has a Cartesian product, right? Oh no, sorry, you're right. Yeah, sorry.
Usually the endomorph
Yeah.
don't have to be commutative.
Yeah, no, you're right. So let me, yeah, okay, you're totally right. So this is, okay, let me ignore that because I'm not going to say anything about the E infinity. I mean, this turns out to be an E infinity ring.
Because it's a special.
Yes, you're right. Sorry. Stefan is right. Sorry, I just incorrectly stated that it follows from abstract nonsense that this is an E infinity ring. But since I can't say anything about the E infinity ring structure anyhow, let me just take that back and talk about just the spectrum. The first thing I'm going to say is the spectrum is a direct sum of KZs. So that's the first part. Second part is...
For the indexing or just that it's sum direct?
Yes, I'm going to tell you what the indexing is, but so a priori, well, let me state what the indexing is in a ringy way, because that's better to say. So the homotopy groups, I mean just unshifted copies of KZ. Like an countable number of unshifted copies of KZ, but let me sort of be more specific. The homotopy ring is given by well, the KZ star, the homotopy groups KZ, and then you adjoin E1, E2, and so on, where the EIs are all in degree 0. And you should think of these as elementary symmetric polynomials. So these are really correspond to the lambda operations that exist in here, but you should think of these as the elementary symmetric polynomials. So that's a ring of symmetric functions on K star Z. Ring of symmetric functions on K star Z. And this is actually known to be the free lambda ring on a single generator. That's how this relates to the theory of lambda rings. And more generally, or like, you can prove similar theorems for the higher mapping spaces, like from n copies to m copies here, and similar statements here. And one way to sort of say that is that the homotopy category of this kind of algebraic theory is just exactly the algebraic theory of lambda rings, classical lambda rings. In particular, if I have one of these spectral lambda rings, automatically for free I will get that pi naught, or the homotopy groups of that spectral lambda ring carry the structure of ordinary lambda rings.
Lambda ring or lambda ring algebras over K star Z?
Well, I guess I said something about the homotopy category, which will only consider pi naught of KZ, and this is the integers. So you're right, so one could somehow do the following operation, take this algebraic theory TFS and replace the sort of mapping spaces by their graded homotopy groups. And then I would sort of have to make a statement along these lines, yes. Okay, but, right, so this is about spectral lambda rings. And let me just say, the first statement is a Devisage style statement, so you can immediately reduce to simple objects, and then these simple objects have been studied by representation theorists. I mean, I've learned most of that from papers of Henning Krause. So it's just a restatement of like certain semi-orthogonal decompositions and stuff people in representation theory have obtained. Okay, good. So now in particular, this is, if you now sort of unfold this proof that the K-theory groups of a scheme or like a ring are actually lambda rings, then you're very close to the proof given by Gillet and Soulet. This is in some sense a higher version of their proof. Okay, so are there further questions? Otherwise, let me exploit one of the things which I find very surprising. Here's a corollary. So if I take KR, for every ring R, the spectrum, and I base change it over K of the integers down to the integers. So that comes down to, this is going to be an algebra by formal nonsense over the base changed algebraic theory. But the base changed algebraic theory is just the algebraic theory of classical lambda rings. So this is actually a simplicial commutative lambda ring. I mean, so it inherits canonically the structure of a simplicial commutative lambda ring. And if you know something about E infinity rings, this is like in general a really hard constraint to have an E infinity ring refined to a simplicial commutative ring. Particularly, you're going to have like divided power structures and stuff like that. And even stronger, if R is characteristic P, then already KR, as you localize at P, is actually a simplicial commutative lambda ring. This again follows with the same argument. You just work over KFP, and then KFP, as I localize at P, is just Eilenberg-MacLane. So it comes down. And this is something I didn't know before, and I don't know if anyone knew that. So it's very surprising. Just for every FP algebra, the K-theory spectrum, as I localize or complete at P, is actually a simplicial commutative ring. Even more, it's a simplicial commutative lambda ring. And this has concrete consequences. For example, you're going to have divided powers on the K-theory groups. So that's kind of a sort of, in some sense, you should consider that as a highly structured version of the argument I gave at the beginning. It's a higher homotopy group somehow. If R is perfect, have to vanish. So was there a question, Stefan?
Did you explain how you get this parallel? Did I miss it?
So what I get is a priori, if I'm characteristic P, I'm going to be an algebra over an algebraic theory where I just replace Z by FP here, right? So like I guess by an extension of the theorem to arbitrary base, or like at least fields. And then, K star FP, as I localize FP at P, as we've seen in the beginning, is just going to be a ZP in degree 0. So this higher algebraic theory is actually just going to be the one algebraic theory of simplicial commutative rings. So it's actually an algebra over the classical algebraic theory of simplicial commutative rings. Not the homotopy groups, but the actual
so the
space.
thing I'm missing is that simplicial commutative isn't an infinity type notion.
Right.
The infinity Lavier theories, that was the point.
So there's two different Lavier theories. There's a Lavier theory of E-infinity rings. And there's a Lavier theory of simplicial commutative rings. The algebras for this are E-infinity ring spectra, or E-infinity ring spectra, connective E-infinity ring spectra, whereas the algebras for this are sort of those things which can be represented by simplicial commutative rings. And in general, if I have an E-infinity ring spectrum, even if it lifts like additively over the integers, it's a very hard condition to lift to gadget here. Particular on homotopy, you have divided powers and more. And so the statement is that this guy, which is a priori here by what I've said so far, canonically lifts to here. Okay. Tyler?
So if you have a simplicial commutative ring, you usually already have kind of divided power operations on its higher groups. What extra structure does the lambda structure give you?
Right. So, it gives you lambda operations. But I guess the question you could have asked is, how do the two interact? Does this give you higher, like, secondary style operations? And I don't know. Yeah. I haven't really explored the consequences of that statement. I guess for the moment you can sort of relate that to some sort of Milnor K-theory statement that you have these like divided powers. So, right. Good. Right. So now this is what I wanted to say about lambda ring structures. So I find this kind of a pleasing way of stating that. And I guess one thing, Björn, or maybe I'm answering that in the question session. For the remaining time, I'm going to prepare ground for next time, because next time I want to talk about Waldhausen K-theory. So let me start by...
Maybe I'll ask a question first. You've unpacked divided power algebras here. Can you get the rest of the Dyrham-Witt complex structure of these things?
Right, so... Right. Right, let's talk about that later. There's going to be a relation, there's going to be a version of that which I call cyclic K-theory, and that will map to what is called TR by the cyclotomic trace. And you can wonder this exact question in this generality, and then there are some very interesting questions which I'm happy to discuss. Right, so let me start by saying a few words about Waldhausen K-theory. So, what's the idea of Waldhausen K-theory? So, idea of Waldhausen K-theory is to just say that K0 is not K0 of a category C is not only group completing pi naught C, but also introducing relations of the form, well, I guess class of A is plus class of C is a class of B for an exact sequence. Exact sequence A to B to C. And for example, in this case of strict polynomial functors from branch C to branch C, I told you they are non-trivial extensions, so we want to sort of not just group complete isoclasses, but we also want to break up things according to exact sequences. And so in general, you could ask, what does an exact sequence mean? And the notion of a Waldhausen category is exactly supposed to make that precise. So what's the definition of a Waldhausen category? This is, well, of course, due to Waldhausen. And in the form, I'm going to say it due to Barwick. So what is a Waldhausen category? A Waldhausen infinity category is a infinity category with a class of morphisms called, well, let me call them cofibrations to stick with a standard terminology. Sorry, Clark. Clark called these ingressive, which I think is actually a good name because cofibration, the notion of cofibration is a little overused in homotopy theory. But still, I want to go with the classical terminology for now. So with a class of morphisms called cofibrations and denoted like this, which contain all equivalences such that the following is satisfied, such that first, well, and I guess I sort of forgot to say a pointed infinity category, sorry. So and in the sense that Emily also meant, like it has a zero object. The pointed infinity category such that first 0 to any object A is the cofibration for every object, and secondly, push-outs of cofibrations exist and are cofibrations. Okay. And then the exact sequences that we care about will just exactly be the cofiber sequence. You just take a cofibration and you push out along the map to 0. And what are examples? Almost. First, additive abelian categories. With monomorphism. Sorry, maybe this like third installment of the morning coffee was too much. Thanks, Jasper. With monomorphisms, with monos as cofibrations. That's going to be a Waldhausen category. And secondly, at the other extreme range of the spectrum, we have stable infinity categories. Cats with all maps, cofibrations. So these are in some sense at the extreme ends of the range of what a Waldhausen infinity category can be. And these are typical situations where we want to form K-theory by breaking up exact sequences. Okay, and I mean there's a lot in between, of course, like in, for example, finite sets, finite pointed sets, maybe I should say that to connect back. Fin star with injections is a Waldhausen category. Or proch R, where you just declare the maps whose cofiber is also projective. So in other words, just the monos of projective modules. The split monos, I guess, of projective modules to be cofibrations. Okay, so what's the point about Waldhausen categories? Well, I mean, the point is, of course, to define Waldhausen K-theory. And essentially, Tobias has already given us a definition, so let me be brief about that, also because my time is essentially over. So if C is a Waldhausen infinity category, then, well, we can, I mean, let me first define the underlying space of K of C. So K of C is going to be a spectrum, and I start by defining its underlying space. How do I do that? I just define that to be the loop space of S dot of C tilde, where S dot is the S dot construction, where Tobias has introduced that S dot. Oh man. S dot, I guess Sn of C is a full subcategory of the functor category from functors delta 1 to delta n into C. So these were like these grids that we had on the board, and then you're going to require that on the diagonal you're 0, and all the squares which come up are like push outs. So in other words, these are all cofibrations, and then the push out exists. Okay, so that's S dot. And why is this a spectrum? I mean, a priori this defines a space, right? So by this like bars, I mean the geometric realization. In other words, the colimit over delta op. And so why is this a spectrum? This is a spectrum because all SNC are, well, symmetric monoidal with respect to coproduct, right? So in particular, being a Waldhausen infinity category implies you have coproduct. So we can make that symmetric monoidal with respect to coproducts. Therefore, SNC tilde is an E infinity monoid. This also implies that the geometric realization SNC is an E infinity monoid. This is because, well, I mean, for those who know what this means, this is because delta is a shifted colimit, and shifted colimits of E infinity monoids are computed underlying. And finally, this implies that omega of that is an E infinity group by an Ekman-Hilton argument, because this has an additional group structure besides the coming from this, one which is composition of loops, and therefore by Ekman-Hilton they have to agree on pi naught, and hence pi naught is a group. Okay, so that defines Waldhausen K-theory as a spectrum. So we can consider Kz as a spectrum. Right, and I guess I'm out of time, so an exercise until next time, if you want to understand this definition, is work out what this means, what pi naught of Waldhausen K-theory is, and how this makes precise breaking up exact sequences. All right, thank you very much.
Yes.
So when you showed how polynomial functors act on the group completion K-theory, you use this universal property of the group completion and some calculation.
Right.
So what replaces that in this context?
So there's this beautiful universal property of Waldhausen K-theory as a functor, which is due to Barwick and in a slightly different setup to Blumberg, Gepner, Tabuada. And so, in fact, you use that as a functor, it has a universal property. Not like, I mean, you know, group completion K-theory has a local universal property. For a given category A, we can exactly say K of A is like the group completion. And Waldhausen K-theory only has a universal property as a functor. As a functor from Waldhausen infinity categories to spectra. You can say it's kind of a group completion. I mean, the universal property is additivity, if you know that. Or like as a functor from stable infinity category, it's a universal functor which splits Verdier sequences. And that's in fact also why I formulated the theorem. I formulated it because the functor from additive categories to spectra also has this exact universal property. It's like universal locally, but it's also universal as a functor. Functor K-theory from additive categories to spectra is actually the universal functor which makes everything group complete. So the universal functor under the functor which just takes the underlying space, which is an infinity monoid, and makes this group complete. So in fact, for the proof, I think personally from my intuition, the local universal property is much more helpful. But for proofs of this polynomial style results, the universal property as a functor is exactly what you need. And yeah, I guess for Waldhausen K-theory somehow, in some sense, the definition is maybe universal property. It gives you a generators and relations description, but there's no like nice universal local property of this sort. At least I'm not aware of one. I guess if Clark doesn't know, then it doesn't exist. Right.
Is the previous theorem you mentioned about the polynomial functoriality of K-theory as a space-valued functor, is that out somewhere?
Well, this is going to be out soon. Yeah. I guess we figured that out like sort of, I mean, I gave the first talk about that a year ago, and sort of several reasons, yeah, but it's going to appear soon. I mean, sort of we somehow had the feeling that we have to explore these lambda rings a little more. So these spectral lambda rings, but it's really hard to sort of actually understand, like, I mean, this is a definition, it's a totally valid definition, and sort of, you know, my other hobby is to work with TR and cyclotomic spectra. This also looks like Witt vectors. So in fact, you can prove these like spectral lambda rings form a plethory over E infinity KZ algebras. This means there's a right adjoint, which you could call the spectral Witt vectors. And so I was actually sort of using a lot of energy into comparing that to TR-style definitions of spectral Witt vectors. But I guess at this point, I don't know, and we're going to just upload it soon. So for example, like the question that Björn raised was essentially, I mean, do I have 1 minute of saying something about that? Sorry, Björn, for ignoring it earlier. So
we just have to eat lunch, you know.
We know, like, if we have K-theory, say, let me talk about KU, because somehow KU we've already seen is essentially K-theory of the complex numbers. So we know we now have on space level, you can prove this is also a spectral lambda ring. So we know on space level we have all these operations, but another thing that is known and that I've used before is if we invert P, then we know there's this E infinity operation, the lambda operation, psi P. And on space level it just exists because, I mean, you can just write down the linear combination that leads to the Adams operation just on space level. But the statement is that this can't be looped to a map of spectra unless you invert P. And so, like, a much weaker answer that one could hope for, I mean, Björn was asking a very strong question, but let me say a weaker question that one could ask is, does one always have such an E infinity ring? If I give you a spectral lambda ring A, is there always going to be an E infinity version of psi P? And I guess by work of a student of mine, Stefano Ariotta, we know that this is true, that we get a map of spectra, and only if we rationalize. But I mean, I expect his methods to go through, so that you get at least a map of spectra as you invert P. But I mean, we are somehow, in some sense, very far from saying there's an E infinity self-map of this sort. Because, I mean, this is somehow a very subtle thing, you know, like writing down the Adams operation and saying these are ring maps is really a computation you do in elements. If you prove that, you know, you have an abstract lambda ring, there's this universal formula for Adams operation, then you prove these are ring maps. And this is somehow telling me that the fact that they are one-fold loop maps, as proven by Grayson, tells me that somehow this proof holds like E1 style, but not E infinity style. Like somehow this elements proof can't be made totally coherent. So, right, so that's, I guess at the moment, so I'm inclined to say we can more or less prove that this exists as an additive map as we invert P, but not as a map of E infinity rings. So, right. So that would be sort of a conjecture that I would raise, which certainly had like serious applications.
Yes.
Do you know anything about the interaction?
You have to speak up, Andrew.
Sorry. Do you know anything about the interaction of this stuff with trace methods?
Right. I mean, this is, yeah, I mean, in fact, this was the main motivation for me to look into that. I think somehow the first person who like asked this question in this form was like Peter Scholze. And unfortunately, there's this weird thing about, okay, so just for those who know a little bit about trace methods, so there's this trace going from K-theory into TC. And maybe there's a refined version of the trace going from what I call cyclic K-theory into TR. And maybe we ignore TC and go down to THH. So there's these weird sort of things called lambda operations on THH. These just come from like covers of the circle. But in my opinion, they don't behave like lambda operations at all. They're just, you know, I mean, just something which rationally looks like lambda operations. But giving a rational lambda ring is something very weak because, you know, like I just told you that a lambda ring is essentially given by giving Adams operations, which are lifts of Frobenius. But if we're rational, this condition just disappears. There's no Frobenius. So it's just going to be, for every prime, I have a commuting endomorphism. So giving a rational lambda ring is somehow, in some arithmetic sense, a very weak structure. So I think rationally, these operations coming from self-covers of S1 look actually like lambda operations, and it's known on homotopy groups that these operations agree. The trace will be a map of lambda rings rationally. But integrally, I don't think this, I mean, even the statement doesn't make sense, because this is not a lambda ring in a highly structured sense. I mean, we can prove that this cannot be a spectral lambda ring. For example, not even on pi naught, this can be an ordinary lambda ring, because, for example, if you input fp, you get fp on pi naught. But you can prove in a lambda ring, the element 1 can never be torsion. Just a formal consequence of being a lambda ring. So this cannot lift to a lambda ring. But I mean, it turns out that TR actually can be made to lift to a lambda ring. So TR is actually in pi naught given by the Witt vectors, if you know what TR is. And so you could somehow ask the question there. But now what happens is somehow cyclic K-theory or TR, this has in some sense two different lambda ring structures. One which comes through the functoriality in R, the process I've described today, and one which is coming from these weird self-maps of S1, which I would not really consider to be an actual lambda ring structure. So the trace is somehow for one of the maps, I mean, like it's somehow this part of the trace would respect like the one coming through R, and this part which somehow respects the one coming through the S1 action. And so I guess Björn has also thought about that a lot, I guess. Yeah, so I guess I'm going to sort of enqueue. So I don't know, I mean, in some sense, I don't know what the statement would be. I guess a better statement you could make, but is that there's certain filtrations coming from lambda ring structures. And so somehow could hope that some derived version of the beta filtration relates to the BMS filtration on TC. That's maybe a sort of, but then you first have to define all these terms. I mean, this is somehow what the project is about. Right.
Yes, Andrew again.
Yes, sorry. The other question.
You have to again speak.
People want to have lunch.
So what happens if you work in not with commutative rings, but with the infinity ring spectra?
Right.
So if you don't expect this in general, but are there infinity ring spectra where you can see this kind of structure?
Right. I mean, a very optimistic. I mean, you know, people. Whitehouse and others have made precise what you could mean by a map lambda n on, say, K of the sphere or K of finite sets, which is the sphere. I mean, this is maybe not the problem because, for example, for a finite set, you could just say the exterior powers, like take all the K, the exterior powers, just take all subsets of cardinality K. That's somehow, in some sense, like an F1 generalization of lambda K. The problem is that they don't satisfy these kind of hard arithmetic conditions which constitute a lambda ring. So what they satisfy is what people sometimes call a beta ring. So in some sense, one could hope that if you form the same exact, I mean, notion of strict polynomial functors and everything like that makes sense over a sphere, but then you would just get a totally different algebraic theory. And one could hope that this would be some spectral version of this beta algebraic theory. And I have no idea how to get my hands onto the computation of the K-theory of this kind of strict polynomial functors onto the sphere. So I mean, all the methods we use just break down, so I don't know, but also in some sense it would be much less useful because it's much less rigid of a structure to have this beta ring structure. So in fact, actually this kind of all this generalizes to simplicial commutative rings. If R, which was a ring, is replaced by a simplicial commutative ring, you still have these lambda operations on the K-theory spectrum, but just not for an, like E infinity ring spectrum.
Good. Thomas also has another talk, so you can ask questions after that. Now, just one thing left before we can eat our lunch. That's to thank Thomas again.